All right, let's finish up electron configurations by looking at elements in the same family, in the same group going down, and what happens when we turn those into ions. Let us start here with lithium. We're going to look at lithium, sodium, potassium, rubidium, and look at the ions Li+, Na+, K+, and Rb+. First, let's draw the electron or write down the electron configuration of the element itself. If we have lithium here, we see, okay, here's lithium on the periodic table, N equals 2. The previous noble gas was helium, so using this shortcut, we will do helium core 2s1. I'm going to go down right now to sodium. Note sodium is right here under lithium. That would be neon core 3s1. Potassium is right under sodium. Argon core 4s1. And finally rubidium down here, krypton core 5s1. Recall way earlier in the semester when we talked about the reactivity, how when Mendeleev was putting together his table, they noticed that lithium reacted a lot like sodium, and which react a lot like potassium. All these guys reacted this very, very similarly. Question, why do they react so similarly? Look at their electron configurations. Each one of those has one electron in the outermost shell. It has not only just one electron in the outermost shell, each one has one electron in the s orbital of the outermost shell, and that's the only valence electron that it has. But what happens if we make it a positive charge? Okay, what if we take a lithium atom with its 2s1 electron, and we remove an electron? Which electron are we going to move or remove? We remove the valence electron. So Li+, the element plus, is just going to be helium core for lithium. Sodium, that's just neon core. Potassium will just be argon core, and rubidium will just be krypton core. You remove that one valence electron, you're just left with the previous shells being filled, but the valence shell, the N equals 2 shell for lithium, the N equals 4 shell for potassium, no longer having any electrons in them. Alright, what happens when we make ions though? When we make anions, let's look at oxygen and sulfur and selenium. I'm going to go this way. What happens here? Well, we'll just do O2- first, do it the long way, and then we can see what's going to happen to the other ones. Normally the electron configuration for O2- will be helium core 2s2 2p 2p4. But now we're going to make O2-. Where will those two electrons go? Well, they will fill up that p shell, that p subshell, and so we will get helium core 4s2, helium core 2s2 2p6. All right. Now, some will come along and say, wait a minute, helium core 2s2 2p6, isn't that the same as neon core? So couldn't I have just written this whole thing as just neon core? The answer is yes, you are allowed to do that. I prefer not to do that because I want to see the valence electrons. All right. When we look over here back with lithium and sodium, we write this as helium core because we know that once we take away this 2s electron, we're at the noble gas core. We can't take any more electrons away. It costs too much energy to take away an electron from this helium core. if you've already taken one of the s electrons away from the next, one of the electrons away from the next higher quantum number, the next principal quantum shell. The problem here is if you write this as neon core, for O2 minus, if you write that as neon core, it kind of lends one to believe that you cannot take any electrons away from that. That, oh, we've got the noble gas core, none of those electrons are available. When in reality, O2 minus still has these 8, the 2 here, the 6 here, the 8 valence electrons that it can use for reactions. It can do some chemistry with those. So I prefer to write this as helium core 2s2 2p6 to indicate I know there are still 8 valence electrons for that O2 minus. Whereas if you wrote it as neon core, that might lend you to think, oh, I can't do anything. Once oxygen becomes 2 minus, you can't do anything with it because it's just like a noble gas. When in reality, you can. That being said, I know there are chemists who do write it as neon core because it is isoelectronic, has the same electron configuration as the neon core, and so that is acceptable. I don't like it, but it's acceptable. All right, so next one, what do we have? S2 minus right under the oxygen. Can we see that that will be neon core? And we'll just take taking the shortcut there, but note that's going to be neon core 3s2 3p 1 2 3 4 3p4, but we're going to add 2 more, so that'll be 3s2 3p6. Se2 minus is going to be isoelectronic with krypton, but I'm not going to write krypton core, I'm going to write argon core. Ooh, this is fun. Argon core 4s2 3d10 4p6. And some might argue, wait a minute, O2 minus, S2 minus, Se2 minus, in the same family, they should have the same reactivity, but Se2 minus, we have these 3d10, those 10d electrons in there. Aren't they going to cause trouble? And the answer is no, they are not, because note, we have filled up the 3d level at this point. So this 3d n equals 3 shell is completely full. We're not going to break into those 3d10 electrons. We're not going to worry about them. There are some books, some people who would actually put the 3d10 electrons over here and write argon core 3d10 4s2 3p6 to indicate that we're not going to break into that n equals 3 3d shell. All right. Well, now things are going to get a little bit crazier. When you deal with transition metals, we've got more stuff we have to worry about here. Recall the transition metals could get a little crazy at times anyway. Now let's look at what's going to happen when we look at transition metal ions. The best way to deal with transition metal ions is to write out the electron configuration of the transition metal as if it was a neutral atom, and then figure out what you have to do to it to make it the ion. So first thing, let's look at iron 2+. The first thing I'm going to do is just look at the electron configuration of iron itself. Iron, well, here it is on the periodic table right here, would be argon core, got that, 4s2, 3d 1 2 3 4 5 6, 3d6. So there's the electron configuration of iron. The next question is, when we make iron 2+, what 2 electrons are going to leave? Now, what your mind is probably telling you right now is, well, since we put in these d electrons last, perhaps 2 of these d electrons leave to make this 3d4. Turns out that's not the case. With transition metals, once you start putting electrons into the d orbitals, this is important, once electrons actually are going into d orbitals, they become lower in energy than the s orbitals. Before you put any electrons in those d orbitals, they're actually higher in energy than the s orbitals are. But once there's electron density in them, these 4s electrons become higher in energy than those 3d electrons, which means with transition metals, you always take the s electrons first. So iron 2 plus, we need to remove 2 electrons. The highest energy electrons are actually these 2 electrons for 4s. So Fe2 plus is going to be argon core 3d6. It's the 4s, those 2 4s electrons are the ones that get taken away. All right, but what about iron 3 plus? Well, iron is argon core 4s2 3d6. Now we need to take 3 electrons away. The first 2 electrons come out of the 2s, or excuse me, the 4s orbital. Those 2 electrons come out. We need to take 1 more electron to get 3 of them taken out. That means now we'll take away one of these 3d electrons. So iron 3 plus gives us argon core 3d5. We took away both 4s electrons and then one of the 3d electrons to make argon 3 plus. All right. What about chromium 6 plus? Well, I start out by saying, well, what about just chromium itself? What if we're looking at neutral chromium? That would be, well, here's chromium here. That's argon core 4s2 3d 1 2 3 4. 3d4 is what we would initially put, and then we'd realize, oh, wait a minute, 3d4, put 1 more electron in those d's, and that would be 3d5, and that's a half-filled subshell, and that is stable. Oh, that's right, chromium puts one of these s electrons up here, so this is actually not the right answer for chromium. The right answer for chromium is argon core 4s1 3d5. Cool. But now we're going to make chromium 6 plus. We have to remove 6 electrons. What 6 electrons get removed? Well, could you see if we're only removing 1 electron, if we're only making chromium 1 plus, we would get rid of the 1 4s electron. That would be the first to go. But we're getting rid of 6 electrons, which means 5, the 4s, 1 4s electron, and the 5 3d electrons, all of those get taken. So chromium 6 plus is just argon core. Note that chromium 6 plus, you cannot remove another electron from chromium 6 plus because we're in argon core. We've gotten rid of all its valence electrons. It had 6 valence electrons. We've gotten rid of those. And we're down to argon core, so it has no valence electrons. And breaking up that argon core when your molecule or your atom already has a 6 plus charge takes an extreme amount of energy to do. It's not going to happen under most normal circumstances. In fact, chromium 6 plus is in a very high oxidation state. Recall oxidation states. That's a pretty high oxidation state. So high in oxidation state that chromium 6 plus really wants electrons. It makes it a very good oxidizing agent because it will take electrons from anything, just about anything. All right. Well, now let's go down to silver plus. Start off with silver, just a silver atom, and silver is right here. And so let's look at this. This will be krypton core. And we would start out krypton core, 5s2, 4d9, 1, 2, 3, 4, 5, 6, 7, 8, 9, yep. And then we're like, uh-oh, silver, 4d9, no, it's not going to do that. Recall, it's going to take one of those s electrons to give us krypton core 5s1 4d10. Fill up that D shell. All right, but that's just silver. What electron will get taken away when we make silver +1? Right now you should all be thinking, that 5s electron is going to be the higher energy electron. You are right. Krypton core 4d10 is the electron configuration for Ag+. Note, we still have the 4d10, we still have that completed filled 4d subshell. Because of that, because that's so low energy, it turns out that silver +1, the +1 charge, is the only oxidation state we get for silver other than silver 0, metallic silver. Silver is only going to form +1 ions, or it's going to be silver metal, because of this very stable krypton core 4d10 electron configuration. All right, our last electron configuration for the video, uranium 3+. Okay, well, where's uranium on the table? Oh, that's right, it's way down here. Here's uranium, right there. Well, well, how are we going to start this off if we have uranium 3+? We're going to start off by, what would uranium be? Just regular uranium. Can we see that is radon core, 7s2, 6d1, 5f123, 5f3. That's just regular uranium. If we make uranium 3+, the question is, what 3 electrons do we take away? Well, what would your guess be? Right now you should probably say, well, I bet we take those 2 7s electrons away, right? Yeah, those are the first 2 to go. When we're making 3+, we have 1 more electron to take away. Which 1 electron is left to take away that looks like it would be a good candidate? It's that 6d1 electron. So uranium 3+ is radon core 5f3. Note that all of these guys here, all of 90 through 103, their electron configurations include 7s2, 6d1. Note that all of these guys here, cerium through lutetium, they're all going to have 6s2, 5d1 in their electron configuration. It comes as no surprise, hopefully, that what we find in nature is the +3 oxidation state is very common in all of these elements. And most of these elements, you see the +3 oxidation state as a fairly common oxidation state for these guys, because when you take any of these guys and do the +3 oxidation state, you get rid of those higher energy s electrons and that higher energy d electron, leaving only f electrons left.